Tangential and angular motions are part of a broader topic called circular motion. And circular motion does tend to be a little bit of a challenge for students. It tends to just kind of tie your brain up into knots and hard to perceive. So let's stick with it from the very beginning and see what we can do. First thing we're going to do is just simply take care of a couple vocabulary words. And the one word here is rotation. And it's simply when something's spinning, the axis is located within the object itself. So a soccer ball could be spinning around like this, and this is the axis. And revolution would be the counterpart to that, but this is a spin where the axis is located outside of the object. So the ball could be revolving around this axis or rotating about that axis. And then, of course, the Earth will both rotate and revolve. It rotates about its axis, it revolves around the sun. But let's just diverge here for a little bit and look at the period of its rotation. Now, we could use a lowercase t for just any old amount of time, but if it's the time for a complete rotation, we use a capital T here, and that stands for the period. And the period of rotation is 23 hours, 56 minutes, 4.09 seconds. And I bet you thought the period of rotation was 24 hours. That fact alone does not explain leap year, although some may think it does. The period of Earth's revolution around the sun is 365 days, 6 hours, 7 minutes, 38.0 seconds. It's 365 days and pretty close to a quarter more. That explains leap year, why we add an extra day to February. But I'll diverge here even further for a moment. That fraction there is almost a quarter. So every 4 years you got to add in an extra day, but it's not quite a quarter of a day. So if you add in an extra day to February once every 4 years, by the time 100 years have gone by, you've added in one too many days, so you take a day out of February. If you take out a leap year once every 100 years, by the time 1,000 years have gone by, you've taken out one too many, and you got to add it back in. A little confusing. Okay, so let me see if I can explain briefly why the period of rotation is about 4 minutes shy of a 24-hour day. If you're standing right here on Earth and the sun is directly over your head, that is noon. It's high noon. And if we just look at Earth's rotation, the time from high noon to high noon is 24 hours. That's the definition of a day. But the Earth isn't just rotating. As it rotates, it also revolves. So here, one complete rotation is when this line here gets back to level and horizontal again. So that was one complete rotation. It takes this much time. But we're not quite back to having the sun be directly overhead. It takes an extra 4 minutes to get the sun directly overhead. Just a little connection to the motion of our planet around the sun. I hope you know the definition of 1 degree. It's simply 1/360th of a rotation. And if you've had pre-calculus or algebra 2, you might be familiar with another unit to measure angles. Just like we can use metric system or the imperial system to measure length, there are different units to measure angles. And a radian would be another unit we could use to measure angles. And if you've had algebra 2 or pre-calculus, you probably are familiar what, say, pi radians are, about 3.14 radians. That would be the same as 180 degrees. Or pi over 2, half of 3.14. That'd be about 90 degrees. But what's the definition, the very definition of 1 radian? Well, it's an angle whose arc equals the radius. And that may not make much sense until we draw a little diagram here. So here's the radius from the center out, and if we rotate through some angle here, the arc is the length of that curved line there. when the length of the radius and the length of that arc are equal, the angle that is formed is called 1 radian. So defining a radian in terms of the length of the arc and the length of the radius, it is going to really make our life a lot more convenient than simply using degrees. 1 radian is about 57.3 degrees. So there's the beautiful relationship, just based on that simple definition. Remember, if the length of the arc is equal to 1 radius, we have 1 radian. If the length of the arc were half the length of the radius, well, that angle would only be half a radian. Or if the length of the arc were twice as long as the radius, then we'd have 2 radians. So it looks like whatever fraction the arc is in terms of the radius is, that's going to be our angle. So S equals r theta. S is for arc length, and it's curved like an arc. Radius, and then theta is our symbol for the angle. S equals r theta. If this here is twice the length of the radius, then we would have had 2 radians. Well, then the question is, how many radians are in one rotation? So that's 1 radian, and that's 2, 3, 4, 5, 6. It looks like it's a little more than 6 radians all the way around. Well, we can find it by just taking that equation and solving for the angle. The angle is going to be the arc length divided by the radius. So the distance, the number of angles all the way around, would be the length of the arc all the way around, which is known as the circumference, and we're going to divide it by the radius. It's how many radii fit into the circumference, and we just get 2 pi. So the angle all the way around is 2 pi radians. And let's look at the unit of a radian. Okay, we had 6.28 is about 2 pi, 6.28 radians, but what's the unit? Well, it's funny, and this is probably the only unit that's like this. It's a unit that is not a unit. It's a unitless unit. Because if we measure the length in meters and the radius in meters, meters cancel, and there are no units. Radians is just a number. We call it radians, but it really is not a unit. Okay, so if we measured this in feet and we had, say, 3 radians, 3 feet times 3 radians is just, 3 feet times 3 radians would be 9 feet along the arc. If we had measured the angle in degrees, it wouldn't work out that way. If we had, say, 2 feet of the radius and 75 degrees, it would not be 150 feet along the arc. So they would just be proportional. If you double the angle, you would double the arc length. All right, so that's angular distance. Now let's look about an angular velocity. Angular velocity, and we use the Greek letter omega. Sometimes I say it's wangular velocity to help us understand that we use omega there. But it's just the change in the angle divided by time. So if this is our thing, and we're going to rotate this at 90 degrees per second, that's 1 second, 2, 3, 4. It's going to take 4 seconds to go all the way around. We went 90 degrees in 1 second, or 360 degrees in 4 seconds. Notice I'm using a lowercase t for just any time, and a capital T for the time to go all the way around. If we're going to have an angular velocity of 60 degrees per second, we'll go 60 degrees in a second, and another 60 in a second. That's 3, 4, 5, 6 seconds all together. But we can measure angular velocity in radians per second. So remember, it's about 57 degrees. So if we rotate this thing at 1 radian per second, that's 1 second, 2 second, 3, 4, and I lost track, but it's going to be about 6.28 seconds. 1, 2, 3, 4, 5, 6, 0.28, that's 2 pi approximately. If we rotate at 2 radians per second, so we start 1 second, 2 seconds, 3.14. Okay, 3.14 seconds all the way around. So we can talk about an angular velocity as well. Now if we have a circle and we have a line extending off in either direction, that line intersects the circle in 2 points. We call it a secant. If that line were to move off to the right, those 2 points would get closer together. And if we move that line all the way so that those 2 points were so close together they are one and the same point, that would be considered or be called a tangent line. And the tangent is going to be perpendicular to the radius at the point of tangency. So we measured an arc length, the length of that arc, but in my picture here, this tangential length is the same length. Okay, so we can measure a length along the arc, or we can measure an equal length off the tangent. And this was just a smaller angle. That length and this length are the same. This arc length and that tangential length are also the same. So, well, let's just do it this way. If I take S equals R theta and I divide this side by time and I divide this side by time, well, the angle divided by time is the angular velocity. So this angle divided by time is the angular velocity. But if I take the length along the arc divided by time, well, I'm going to get what we'll call a tangential velocity. So the tangential velocity is going to equal the radius times the angular velocity. And the tangential velocity is just how fast this car is going around the turn here, or how fast that car is going if it just straightened out and went off tangent. Here's what I mean. Let's say if the car is going 40 miles per hour, it's going 40 miles per hour, 40 miles per hour, 40 miles per hour, and right here it just straightens off and goes off tangent at 40 miles per hour. It would have traveled the same distance along here as it did there. So we can talk about, I guess we could talk about an arc velocity. We never really use that term, but more often we use what's called a tangential velocity. Just how fast the car would be traveling if we straightened off and went tangent to the path. So, and because of this clever definition of an angle in radians, this equation works. And then if this is an angular velocity, I just have to multiply it by the radius to get the tangential velocity. And then if we've talked about length and velocity, we might as well talk about acceleration. So let's talk about an angular acceleration. We use the Greek letter alpha for angular acceleration. So we could accelerate this thing at, say, 10 degrees per second, which means every second we will change the angular velocity by 10 degrees per second. So we start off slow, and then we start going faster and faster and faster and faster and faster and faster and faster. That would be an angular acceleration. So an angular acceleration is just a change in the angular velocity divided by time. So if I take the previous equation and now divide both sides by time, an angular velocity divided by time would be an angular acceleration. And tangential velocity divided by time would be a tangential acceleration. The beauty of measuring the angle in radians is we can easily convert from an angular motion to a tangential motion. An angular distance to a tangential distance. An angular velocity to a tangential velocity. An angular acceleration to a tangential acceleration. So we just showed you an angular acceleration, but a tangential acceleration would be like starting and then going faster and faster and faster and faster along that arc, or just going faster and faster and faster tangentially. All right, now we've looked at all of our kinematic equations. Way back in just the first unit of kinematics, these equations, the relationship between these variables. Okay, but now we're just going to look at the angular counterpart to these equations. If we start off with an initial angular velocity and then begin to angularly accelerate for a period of time, we can figure out what our instantaneous angular velocity is. And then same thing here, if I start out at an initial angle, and I guess what do I mean by initial angle? A lot of times our initial angle is 0, but we could have started off at, say, 20 degrees initially. And then we accelerated, and then we had some initial angular velocity to start, and then we accelerated. Okay? And then this is just going to be the same thing here. We're just, for every tangential idea, we have its angular counterpart. All right, let's see if we can just practice this equation in particular. Velocity equals radius times angular velocity. So these things are going around the circle here, and of the three variables here, radius, tangential velocity, or angular velocity, what do all three of those shapes have the same of? And they have the same angular velocity. They're they're revolving through the same number of angles every second. So what's nice about this is that tangential velocity is just the circumference, that's the distance all the way around, divided by the time all the way around. That's its period. If you doubled the radius, you've doubled the circumference. So if you double the circumference in the same and do it in the same amount of time, you've had twice the velocity. So this red one here has twice the radius of the green one. It has twice the tangential velocity. Okay, so twice the tangential velocity there. All right, and anytime we have a solid object, I know we have an old record player here, but anytime we have a solid object where everything's moving in unison, everything has the same angular velocity. If we had two solid things with pulleys, and the things are rotating around here like this, and the outer pulley is twice the radius of the inner pulley, how does the tangential velocity of that belt compare? Well, you can't really see those belts moving, so we just put some objects on it so you can get a reference there. And let's see that they are rotating at the same angular velocity. But when those things fly off tangent here, they have the one that had twice the radius had twice the tangential velocity. And that's just using this equation. Everything had the same angular velocity, but the bigger radius had a bigger tangential velocity. All right, in this animation, if you stare at it too long, you get dizzy. But of those three variables, what do they all have in common? And it is the same tangential velocity. And we can see when they get right there, they were all traveling tangentially the same speed. So if they had the same tangential velocity, what's the relationship between these two variables? Well, they're going to be inversely proportional. If this number gets bigger, that number has to get smaller to keep that the same. So the one here with twice the radius of this one had half the angular velocity. Okay, this one's going around twice as fast as this one, or this one's going around half as fast as this one. And that's just like why they stagger the start in a track race. These all the runners would be, if they're matched evenly, would be running with the same tangential velocity, but they would be running different distances if they all started in unison. And in this thing, what of the three variables do they have in common? And they all have the same radius. And this is kind of easy, that if they had the same radius, the tangential velocity and the angular velocity are going to be directly proportional. So you double one, you'll double the other. And that's just like if race cars, they're all going on the same radius, the same racetrack. The one that goes faster tangentially will also be going faster angularly. You could take two styrofoam cups and tape them together and then race them down these rails like this. But when you do that, both cups have the same angular velocity. Okay, they're just moving in unison. But when the rail touches here on a small radius, same angular but smaller radius, there'd be a smaller tangential velocity. You could tape the two cups together like this, and there'd be the same thing. But if you raced both cups down these rails, one will be able to make it to the bottom, and the other will be absolutely impossible to make it to the bottom. And the reason is, let me come back to this example for a second. If this cup would need to turn to the left to get better centered, and because this is going faster tangentially than this side, it's going to turn it to the left. This one also needs to turn to the left to get better centered, but because this side is going faster tangentially than that side, it would actually be correcting to the right. It'd be correcting in the wrong direction. So this one could kind of wiggle back and forth, and touching on a small radius, it would zing around there, and touching on a small radius, it would go that way. But this one would just be doomed from the start. If it got off a little bit, it's just going to get even further off. These are train wheels. And you may have never noticed this, but train wheels are tapered slightly like this. So this would be two train wheels tapered very similarly to that. So just like those set on two rails, the train sets on two rails. And if the train takes a turn like this, the inertia of the train wants to take it straight, and the rails veer to the right. Well, now the rail is touching on a larger diameter, and now the rail is touching on a smaller diameter over here. That larger tangential velocity on the outside is going to make it curve around. The train stays centered on the rails. This is called a parallel roller ruler, that you could make a line here and roll it backwards, and as long as it didn't slide on the paper, you could draw another line and it would make those two lines parallel. To make that work, the diameter of that black wheel where it touches the paper has to be exactly the same as the diameter of that one, so they've moved the same distance. All right, how do you use that thing? Let's say that you are sailing and you want to sail from here to over there, and it's cloudy and you can't quite see where you're going, so you want to know what heading to take. So you take your parallel ruler and draw a line right on the map, use a pencil, and then just roll that thing straight backwards like that over the compass rose, centering right there, draw your line, pull that away, and look at the heading right there. So if that heading is 260 degrees, you just orient your boat so that that's pointing at 260 degrees, and you'll sail right there. Now the parallel ruler isn't used as much because, you know, if you had to do it over here and roll it backwards, you wouldn't hit the compass rose. So this is a parallel ruler that would do that for you. When a car goes around a turn like this, the outside wheel traveled a greater distance than the inside wheel. It had to be traveling faster, which puts the wheels at a different angular velocity if they had different tangential velocities. That's where the differential comes into play. A differential allows this wheel and this wheel to turn at different speeds and still give power to both wheels. Pretty clever design. A lot of times people take their stock Jeep with 29-inch tires and put larger tires on, maybe 33-inch tires. The problem with that is if these tires rotate around one time, they've gone some distance. If this rotates the same distance, it didn't make a full rotation. And if it did make a full rotation, it would have gone a little bit further distance. The problem with that is that your speedometer is based on the angular velocity of your tire. The faster those spin angularly, the faster it reads your speed. So It turns out to be a simple proportion here. These tires are not going to be going as fast angularly as these tires, even if those two cars are going 75 miles per hour down the highway side by side. And it does turn out to be a simple proportion. Your speedometer is geared toward 29-inch tires. What would your actual speed be if you had 33-inch tires? And you just cross multiply there and solve. But when your speedometer reads 64 miles per hour, you're actually going 74 miles per hour. Something you want to know if you put on bigger tires. And if you have a flat tire and you just have this little donut, a spare tire, you don't put that on your tire and drive 75 miles per hour down the road, because if this tire is going 75 miles per hour down the road and that tire is going 75 miles per hour down the road, and you're on the opposite side, they have the same tangential velocity, but the one with a much smaller radius is going to have a much bigger angular velocity, and that will be spinning a lot faster than the tire on the other side, and that's kind of hard on the differential. It can overheat. All right, the Earth is a solid object that rotates in unison. So every place on the Earth has the same angular velocity, an angular velocity of about one rotation every 24 hours. It was 23 hours, 56 minutes, 4.09 seconds, but that's okay. 24 hours close enough. So if you're standing here, you're going to have a different tangential velocity than if you stand here. In fact, if you're there, you're going about 1,000 miles per hour to be able to go all the way around that in 24 hours. Okay, so everywhere on Earth has the same angular velocity, but different radii, not radius to the center, but radius to the axis. Different radii would have different tangential velocity. So what? Well, that relates to the Coriolis effect, that if we had air sitting next to the surface, the air is not moving. And so the velocity of the air and the velocity of the ground are the same. Okay, but if that air, and the ground here, because it has a smaller radius, has a smaller tangential velocity. So if that air moved north, and it's due to its inertia, it keeps the same tangential velocity. Now we have wind, where before we didn't. So right now the air is moving with the ground, and if that air were to drift northward, it's going to start moving relative to the ground because it's trying to keep its same tangential velocity. As the ground has a smaller radius, it would have a smaller tangential velocity. That helps us understand weather patterns. If storms come from the south and move north, typically those storms are going to be moving to the east across America. And that's part of what's called the Coriolis Effect. Another example of that is this is a device that is shooting water out like this, shooting water toward the center, and there's a spigot here that's shooting water out to the rim, and the whole thing will rotate. But watch what happens to the water as it rotates. It seems like it curves. Okay, in slow motion here, right there. Okay, there we go, in slow motion. To the side there. What's happening here is that the water was being shot that way, but because the whole thing was spinning, it had some tangential velocity that way. And as that water shot, its inertia wanted to keep the same tangential velocity that way and that way. And this rod here, because it had a smaller radius, had a smaller tangential velocity. So it's the rod that's slowing down, and the water just kept going with the same speed. All right, that brings us to the end here, where we have our regular kinematic equations and the angular counterpart to each of those. One thing I didn't mention earlier is those are the equations we developed, but if you wanted to convert this into that, that's how you do it. Each of those would be conversions from an angular motion to a tangential motion.